Hi, this is Mr. Manley. In this video, we're going to look at the graph of a logarithmic function and the domain, the graph of a log function. And we'll look at how you could find the domain without actually graphing it. But let's start off with graphing. And as with all graphing, we are going to go ahead and set up an XY axis. And if you remember from the graph of an exponential function, we just really need 2 points here. So remember, with an exponential function, we needed the horizontal asymptote, and then we needed 2 points, and then we had the exponential function. So this is for exponential, okay? For a logarithmic function, we need a vertical asymptote. It's a vertical asymptote, and then 2 points, and we've got our log function. So that would be a log function. So the vertical asymptote is found right here, and it is found by setting the argument, that is the value in parentheses, equal to 0, and then solve for x, and that tells me where the vertical asymptote is at. And then I could graph that. And if I don't have just think, if I had, let's just look back here. If I had this, if I just had that, log of x, then the asymptote, the vertical asymptote, is at x equals 0, the y-axis. And then if I had, say, this, and if I were to set that equal to 0 and solve for x, I'd see that the vertical asymptote is at x equals 1. So hopefully that's simple enough for you. Now let's put it back to what it was. It was plus 2, I think, is what we said. Or was it minus 2? I think it was minus 2. I don't remember. But we're going to say that it's minus 2, and that's going to put the vertical asymptote at 2. And then I just need 2 points, and I want to choose convenient points, just like we did with an exponential function. Now it might seem like, well, maybe a convenient point is 2. But we should be able to see that that's not the case. I mean, it looks good, maybe, because it makes that come out to 0. But then if I keep looking over here, I see, oh, well, what's happening at 2? At 2, there's an asymptote. So nothing is happening at 2. The log function is undefined at 2. So this is something that we could reason out by what we've done up to this point. And also you can just add to your notes that log of 0 is undefined. So that's something that we should know. And in fact, and then for another one, log of -1 is also undefined. So we're getting that we can't do logs of negative values, can't do log of 0. Okay, so what is the convenient value? Well, if you understand how logs work, you know that we would like to choose a value of x, so we would like a value of x such that the argument, the value that we're doing the log of, is 1. So let's look at what happens there. G of 3 is equal to 3 plus log base 2, and then when I do x is equal to 3 here, that's going to be 3 minus 2. So I'll have log base 2 of 1. All right, what's log base 2 of 1? Log base 2 of 1. That is the power to which I would raise 2 in order to get 1. That's how I evaluate this. The power of 2 that equals 1. So think about that for a moment. 2 to what power is equal to 1? Okay, well, hopefully you can find your way to 0 on that. 2 to the 0 is equal to 1. So log base 2 of 1 is equal to 0. So you see how that's a convenient value if I can set myself up so that I'm looking for the log of 1. So log base 2 of 1 is 0. So that's going to be 3 plus 0 is 3. And that's one convenient point. All right, now watch for my second convenient point here. My second convenient point is going to be when I have log base 2 of 2. So I'm using 4. Now look what happens when I do that. G of 4 is equal to 3 plus log base 2 of 2. Okay, what's log base 2 of 2? Log base 2 of 2, all right. Power of 2 that equals 2. So what power of 2 equals 2? 2 to what power is equal to 2? What's 2 to the first power? So log base 2 of 2 is 1. And with that, we'll have 3 plus 1, which is 4. All right. Now this is pretty coincidental here that I got 3, 3, and 4, 4. Definitely don't want to get locked into thinking it always works out like that. It just worked out like that this time. So I plot those 2 points, 1, 2, 3, 3, and then 1, 2, 3, 4, 4. Got my 2 points, and then I just curve towards the asymptote and away. And that's the log function. So same idea, an asymptote and 2 points. And we want to look for we want to use convenient points. Let's just take a look at if I just varied the base here, okay? And by the base, I mean this number right here. So that's all I'm going to change. I'm going to change that, and let's say that I just change it to 3, okay? So what do I want to do for my convenient points now? First of all, just notice that, you see, I still have x minus 2, so that's still an asymptote at x equals 2. Now it's just the convenient points that have changed. All right, can you guess what the first one is going to be? How about x equals 3? So that would be g of 3 is equal to 3 plus log base 3 of 1. Right? That was the same convenient point we had before, right? We used a 2, or we used a 3 when we had base 2 as well, right? And just like the other one, I'm looking for log base 3 of 1, and just like the other one, I'm saying the power of 3 that equals 1, and it's the same as before, it's 0. So log base 3 of 1 is 0, 3 plus 0 is 3. So there we have that point 3, 3 again. Now take a look. Can you guess what the next convenient point is going to be? Now remember last time I wanted to get this so that it came out to be 2. So I used 4 minus 2 is 2. And then that made it easy to do it was easy for me to do log base 2 of 2. Now what do you think I want to do here? Log base 2 of 2 was easy. So log base 3 of what? How about log base 3 of 3? So I'll use an x as 5. When I plug in a 5 here, that'll be 5 minus 2 is 3. So that's g of 5 is equal to 3 plus log base 3 of 3. Now what's log base 3 of 3? Log base 3 of 3, if you're following along up to this point and understanding, I hope you know that's 1. Log base 3 of 3 is 1. So that's my second convenient point. And then I plot those points, 3, 3, and 3, 3, and 5, it's not 5, 1. So log base 3 of 3 is 1, but that is giving me this plus 3, so it's 4. So I want 5, 4 here, not 5, 1. Okay, so applying that point, 1, 2, 3, 4, 5, and 4, like that. And there I approach the asymptote, and there's my log function. Just to help you review logs a little bit more, and this is not necessary, but just to help you review logs, what if I said log base x of, what would be the next convenient value? I would say 11, and look at why. Because if I go g of 11, I'm going to have 3 plus log base 3, and what happens when I plug in 11 here? 11 minus 2 is 9. And then how are we evaluating that? What's log base 3 of 9? I'm going to say power of 3 that equals 9. So what power of 3 equals 9? 2, of course. So log base 3 of 9 is equal to 2. And I would have 3 plus 2, which is equal to 5. So that's just another point just to reinforce how the logarithms work. How about just one more? What if I did something like 6? Just showing that this is not a convenient value. G of 6 is 3 plus log base 3 of 6. And I'd go the power of 3 that equals 6. Well, I don't know that. I mean, 3 to the first is 3. Well, that's not enough. And then if I did 3 to the second, that'd be 9. That's too much. So it's somewhere between 1 and 2. Not a convenient value. I could do something with a calculator. I could say, well, it's between 1 and 2. Maybe it's about 1.5. But that's why we want to use convenient values if we can. And again, where we're at is we've got the vertical asymptote and the two convenient values. And we also see that the vertical asymptote gave us the domain because we know all the values need to be greater than that. So I'm going to say that my domain here is from -2 to infinity. So you can always find the domain by finding out where the asymptote is, just like you could use the asymptote to find the range of an exponential function. So that's it. Graphing a log function, reviewing the log operation, and finding the domain of a logarithmic function.